All right. So 2, 4, we're going to find the zeros of polynomials. Okay, so first of all, what is a zero? Okay, yeah, so where the function crosses the x-axis. And polynomial, what does that mean? Many terms. Okay, so we're going to be doing something with something that probably has a high exponent, probably like an x to the 4th polynomial. Okay. So we're going to start this out with the rational zero theorem. You weren't.
I was at first.
All right, so the rational zero theorem. What does the word rational mean?
It's fraction.
A number that you can write as a fraction, right? Okay, so some number that you can write as a fraction. So we're going to find possible rational zeros for functions by using this theorem. Okay. So the way it kind of works, I'm going to kind of write this in a notation. If you have x to the nth plus all these random terms, and then the last term is always the constant term, right? Okay, so what you basically are going to do is you're going to take the constant over the leading coefficient term. So we're going to have the c over the a, and then all the factors with plus or minus. Okay, so let me do an example so you can make sense of that. Okay, so if they're going to ask us to list all possible rational roots, okay, so these are only the roots that can be written as a fraction, of, let's say, our function 2x cubed plus 4x squared minus 2x minus 4. Okay, so first of all, how many possible real roots are there? Okay, there could possibly be 3 real roots. Okay, so real roots implies if I graphed it on the calculator, I would literally see the function crossing the x-axis. Okay, so there could potentially be 3. There could potentially be less than 3. Okay, there could be 2. There could be 1. Yes. N? No, so n is just some exponent. It doesn't even matter what the exponent really is. So to find the possible rational roots, you just take the constant in the very last number and divide by the number that's in front of the biggest term.
So, like, it would be -4 over 2.
Okay, so exactly. So it would be, and I'm not even going to use the negative because in the end I'm going to list plus or minus anyways. So I'm going to ignore the negativity-ness and just work with the 4 and the 2. Okay, so at this point what I'm going to do is I'm going to list all of the factors of 4. So on the top, what are factors of 4? 1, 2, and 4. So I'm going to list those 1, 2, and 4. Okay, and then on the bottom I'm going to list all the factors of 2. So what are the factors of 2? 1 and 2. So my possible rational roots are going to be all of the combinations that create all these fractions. Okay, and then the plus or minus versions of those. Okay, so you could have 1 over 1. You could have 2 over 1. You could have 4 over 1. Okay, and then all those same numbers with the 2 on the bottom. 1 over 2. 2 over 2. And 4 over 2. Yes, Bree?
Why wouldn't you put it
Because in the end, I'm going to list all the positive and negative versions of that. So I'm going to ignore the fact that it's a negative number, because I'll use it in the end either way.
But 2 over 2 is the same as 1.
Okay, so right, so some of these are really going to reduce to the same number. So what I'm going to do is, instead of listing all of these, some of them listed twice, I'm just going to list the ones once. Okay, so 1 over 1 reduces to 1. 2 over 1 is the same as 2. 4 over 1 is 4. 1/2 is 1/2. 2 over 2 is 1, and I already said 1. I don't need to say that again. And 4 over 2 is 2, and I said that already, so I really don't need to say that again. Okay, so really, I have 4 possible rational roots, and then all of the negative versions of those as well. Okay, so I could do plus or minus in front of each of these. Okay, so basically what that means is that of this cubic function, one of these could possibly be one of the zeros. Okay, so I have 8 scenarios where one of these is one of the zeros. Yes. But all of the negative scenarios too. So I could have 1, 2, 4, 1/2, and I could also have negative 1/2, negative 2, negative 4, negative 1.
But I thought there could only be 3 since it's up to the third.
Right, exactly. So it's possible that 3 of those are actual zeros. It's possible that only one of those are possible zeros. It's possible that none of those are zeros. Okay, so this is kind of an interesting theory, I think. Why do they even teach this to you anymore? Because now that you have a graphing calculator, you can just take this function and type it in. Okay, but I want you to understand and really appreciate the way technology has evolved. Okay, back in the 100 years ago, 200,000 years ago, okay, they didn't have calculators, and they had to use these kinds of theorems and then go back and test them. Okay, so how would you decide if one of those was in fact one of our roots? You'd have to plug it in, and what would you have to get if you plugged it in? Yes. What's that? Okay. So lots of years ago, when they started developing math. So what, 1,000 years ago? 12,000 years ago? Okay. So a long time ago. Okay. So at this point, what I want you to be able to do, so they're going to ask you to be able to list these, and then they're going to ask you to then, in fact, find the actual zeros. Okay. So to find our actual zeros, I'm going to let you use a calculator. Okay, so we're going to take these, and instead of guessing and going one by one until we actually found one, we're going to cheat a little bit. We're going to use our technology, and we're going to graph this on the calculator. Hold on for a second. Are we good? Holy cow. All right, so I'm going to type this function into my y equals and graph it. So I have 2x to the third, maybe. Oh my gosh. 2. Plus 4x squared. Oh my gosh, this calculator is really slow. All right, so did everybody come up with this equation when they graphed it on their calculators, or was I the only one that did that?
No, I did that.
Oh, phew, okay, good. All right, so how many times does it actually cross the x-axis? Okay, so we have 3. So we have 3 real zeros, so we're going to find all 3 of them. Okay, so I'm not going to let you just say, oh, the calculator said that it's at 1, -1, and -2. Okay, you're still going to have to prove it algebraically. Okay, so pick one of those, and I'll show you how to do this algebraically. 1. Okay, so we're going to start with 1. Okay, so what we're going to do in order to prove that 1 is in fact a 0 is we're going to use synthetic division. Okay, so I'm going to take 1 and I'm going to plug it into the box, and I'm going to take my function and I'm going to break it using synthetic division. So I've got 2, 4, -2, -4. Okay, so if I drop my 2, what's 2 times 1? Okay, and then I'm supposed to add, what's 4 plus 2? 6 times 1? -2 plus 6? 4 times 1? And so I get a remainder of 0. So is 1 a root? How do I know that for sure? Right, because I got the remainder of 0. Okay, so that proves that 1 is in fact a 0. Okay, so at this point I have a couple different options. I can take the remaining quantity and just factor that out and like set it equal to 0. I could do quadratic formula and solve it that way. Okay, yes? Okay, the other option is that I can go back to my graph and choose another 0 and break it down with synthetic division again. Okay, which is what I'm going to do. You don't have to do it this way, but I'm just going to do it because I think it is very simple. Okay, what is another 0, or there we go, that you can see on the calculator? -1 or negative, okay, so let's go with -1. So this is what I'm going to do. I'm going to put -1, I'm going to use a different color here, in the box, and I'm going to use those numbers that I just broke down. Okay, so now I'm just looking at the 2, the 6, and the 4. Okay. All right, so I'm going to drop the 2. What's 2 times -1? -2, and 6 plus -2 is 4, and 4 times -1, -4, and then I add 4 plus -4 to get 0. Okay, so once I get to this point, what's my quantity that's left here? The 2 and the 4, what is that? 2x plus 4. So I'm just going to take that remaining quantity and I'm going to set that equal to 0 and just solve that for my third remaining 0. Okay, so if you solve that, what's my last 0? -2. Okay, so I can say my actual zeros are at -2, and then I have to go back and list the ones that I proved from the very beginning to say that those are in fact all 3 of my real zeros.
Yep.
Okay. What do you guys think of that? Not too bad?
Not too bad, but
That's not all we're doing. What about, I'm going to throw this out there and see if I need to actually do this question for you. This is another thing they're going to ask you to do, is just to solve the equation. What's that? It doesn't in the, are you going back to the original?
No, I'm going down to average it works.
You're going to which one?
That original problem. So how do you plug in negative?
So, okay, so if you go back to the original function, my initial function, and plug -2 in, then I should get 0.
Well, but that would work for -4. Because any of those could end up.
They could not. So that doesn't mean that all 4 of those are in fact zeros, they're just possibilities. So you so what?
So we don't need synthetic.
Yes, you still have to use synthetic division to prove it. So I want you to, so when they ask you to list the possible rational roots, you're just going to list them. Okay, and then you're going to use your calculator to find the actual roots. So using your calculator, you're going to find a place where it crosses the x-axis, and you're going to prove it to me using synthetic division. I want you to use synthetic division because it helps, because you can break it down further and further. The reason I like that, instead of picking one individually and going back to the original. I'll show you why that's more useful, Josiah. The reason I want you to do it that way is because sometimes you get roots that are not rational, and it's possible to get imaginary roots also that you cannot see on a calculator. So if you are finding an imaginary root, you would have to keep breaking down your function and then use something like quadratic formula or something else to find imaginary roots. Okay, so let me keep going, and I think I'll eventually answer your question. Okay. So what if you were asked to do this? What would you do? Okay, so this time you're not finding zeros. Instead, you're actually solving an equation for the x value. How is this question different from that question before? You're actually solving an equation, but really, other than that, is it any different? Okay, that's true. There's more terms, potentially more answers because it's to the 4th degree, but still you would go about this the exact same way. Okay, so should I go about this? Let's just do it. Let's graph this in the calculator and find a place where it crosses the x-axis and prove that it in fact is a solution. Okay, this calculator is really slow. Will you guys just tell me what you see?
It's like a really huge.
Does it look like a W? Do I need to pull it up? Oh, that's a good idea. Desmos. I don't have Google on here, but that would be a good idea. Did anybody find one yet? Oh my gosh, every time I type something, it just misses it. -5? Okay, I'm going with what Zach said. Anybody else see -5 or at least somewhere close? Let's go with -5. Okay, so let's prove and see if Zach is really right. Usually is, but we'll just prove it for kicks. Okay, all right, so we drop the 1 and then we multiply. So 1 times -5 is -5, and then we add -3 plus -5 is -8. -8 times -5 is 40. -20 plus 40 is 20. 20 times 5 is -100. 84 minus 100 is -16. And -16 times 5 is +80. So, remainder? 0. So, was Zach right? Zach was right, of course. Okay, Zach, did you see any other nice spots? 2? All right, let's go with 2. So Ansel says 2. Let's see if Ansel's right. All right, so we drop the 1. 1 times 2 is 2. -8 plus 2 is -6. -6 times 2 is -12. 20 plus -12 is 8. 8 times 2 is 16. And I do get a remainder of 0. So again, I agree with Ansel. Anybody find another one? 4, okay. So Willow says 4. Let's see if Willow's right. Okay, so I drop my 1 again. 1 times 4 is 4. Negative 6 plus 4 is negative 2. Negative 2 times 4 is negative 8. And I get a remainder again of 0. So I agree with Willow. So what is my last quantity to come up with my very last 0? What does the 1 and the negative 2 give me? X minus 2. So if I set that equal to 0, what is my fourth and final 0? 2. Wait a second. 2? So we got 2 2's?
Bounces.
Ah. Okay, so even without looking at the graph, if we got 2 2's, we should know that that means there's a bounce in the graph. Right? So note to self, when you see a bounce, you can use that number twice. Ah. Because there's 2 of them. Okay? Do you really need to list that number twice as an answer? No, you don't really need to say that number twice as an answer. I'm going to list it because I think it's important information for you to understand. Okay? Bounces you can use twice. Very cool. All right, page 2. Now this is a really interesting little test here that I'm going to show to you. Okay, so this is going to be the upper and lower bound test. Okay, so this is kind of saying where are all of these zeros? What interval do these lie in between? Okay, so what we're going to do is we're going to start by again using the calculator and kind of narrowing it down. Okay, so we're going to start by graphing this in the calculator, which I will do at a very slow pace. Oh, son of a... I think I need to get decimals on here. Almost there. Did it. Yes. Enter. Whew. Okay. Graph. Okay, so for starters, we got an x to the fourth function, so we know it should look like a w. Okay, some kind of a parabola, potentially crossing 4 times, and we can even see the 4 times that it crosses. Okay, so tell me, between which two x values does this look like this function exists between those zeros? Negative. I would go beyond -2 because it looks like it almost hits right at -2. So I would say, what's less than -2? -3. That sounds good. -3 to +6. Okay, so we're gonna say that potentially the interval could be from -3 to 6. Okay, so this is how you prove algebraically that that is actually, in fact, true. Okay, so what we're going to do is we're going to do, again, synthetic division with the lower bound, so the -3. Okay, so for the lower bound, let's see if you can see what happens. So I have 6, -33, -6, 123, -90. Okay, there's going to be a pattern that emerges, so see if you notice what it is. So I drop the 6. What's 6 times -3? -18. So then what's -33 plus -18? -51. What's -51 times -3? Good. 153 plus -6? 147. 147 times -3? 441. Good. Okay, and then 123 minus 441? 318. And what's -318 times -3? And then take that minus 90. Okay. So does anybody notice a pattern that has emerged from doing synthetic division? It's quite subtle. I don't know that for sure. It might be. What? Did somebody else say something? Like, how about the positivityness of them, the values? Yeah, so it just went from positive, negative, positive, negative, positive, negative. Do you see that? Okay, so by definition, if those terms alternate from positive to negative to positive to negative to positive to negative, that tells you that that is a lower bound of the function. Okay, so that's how you can tell if something is actually a lower bound, if you do synthetic division and they alternate. Okay, so to prove something is an upper bound, let's do synthetic division and see what happens with the 6. Let me use a different color, sorry. Yeah. That just the -3 is below all of the zeros. The furthest to the left. It is the lower bound of all the zeros. So lower bound is like, okay, so on the calculator, okay, you see all the places where the function crosses the x-axis, right? So those were existing between -3 being the lower one and +6 being the upper one. So all of the zeros were between -3 and 6.
So this is,
That just confirms that.
okay.
Exactly. Okay. So let me show you what happens on the upper bound. Okay, ready? These are going to be big numbers. I just picked a number that was bigger than the biggest zero on the graph. So if you look at the graph, you could absolutely choose a number way bigger than that. You could use 100.
Isn't the x value 6 though? So it's
I guess we'll find out if we get 0 or not, huh? All right, so we dropped the 6. What's 6 times 6? 36. So you could really come up with an interval that was really big, but just realize that the bigger the numbers that you choose, the bigger the numbers are going to be with synthetic division. So that's why you want to try to keep it smaller or tighter. What's that? Sure, you could use 10. It would, yeah. I guess that would be a little easier. True. Okay. Fair enough. You could use 10. Absolutely. Where was it? Negative 33 plus 36 is 3. 3 times 6 is 18. Negative 6 plus 18 is 12. 12 times 6 is 72. 123 plus 72 is 195. 195 times 6 is 1,170. And minus 90 is 1,080. Okay, so what do you notice about all these numbers? They are all positive. Okay, so if every term turns out to be positive, then that is by definition a proof that that is an upper bound. Okay?
so it's upper and lower.
So negative 3 is the lower because they alternated. And 6 is an upper because all were positive. So that's all of the zeros exist between those two values
Well, this is your general.
of where to find your zeros. Right, which maybe back in the day was pretty valuable. Helped with your guessing techniques. That would be a lot of synthetic division. They probably had lots of dirt. Okay, it does then say to actually find all real zeros. Do I need to go back through and find all real zeros? We're pretty good with that, right?
You just keep going.
Keep going. We just do what we did before. So find an actual, so you said 5 was one of them. We put 5 in the box and find their 0. I don't need to do that again, do I? We got that? Okay, here's another crazy rule. This guy even has his own name on his rule. Descarte. Oops, sorry, I spelled that wrong. Pause. Oh my gosh, I can't spell. Hold on, sorry. Hustle. I'll show you. Okay. So this is really an interesting thing also, I think. This Descartes fella, back in the day before calculators, was trying to figure out some kind of connection about what kind of zeros pop out of a function, some kind of polynomial. Okay, so he started noticing the variations in sign. Okay, so what a variation in sign means is just simply going from a positive to a negative from term to term. Okay, so what I mean by that is from this term to this term, is there a variation? No, because they're both positive. Okay, from this term to this term, is there a variation? No. From this term to this term, is there a variation? Yes. So here's one. I'll put like a check mark to say yes. Okay, is there a variation from here to here? Here, yes. Okay, so how many variations do you see? Okay, so there are two variations, two sign variations. Okay, and what that tells you is how many positive real zeros there could be, and they must be in sets of 2. Okay, so if I see 2 sign variations, that tells me that there could be 2, or what's 2 less than 2? 0. Okay, or there could be 0, positive, I keep trying to write positive with 2 S's, excuse me, zeros. Okay, so a very simple test on this one. Okay, so there could be 2 positive zeros, or potentially there might be no positive zeros. You'd have to graph it to see it, or test numbers in there. But I would probably use a calculator in this century. Where would I get the 0 from? From the calculator. Where did I, what? Say that one more time.
Yeah, where did you get 0?
Oh, that 0?
Yeah.
Oh, because it says, in the definition, it says, or less than that by some even number.
Oh.
So basically, let's say there happened to have been 7 sign variations. Okay, so that means there could be 7 positive zeros, or there could be 5, or 3, or 1. Well, it's decreasing in even numbers. Do you see what I'm saying by that? So it's decreasing by 2 every time. Yes.
So we'll look at the first part. The second part is for.
Right, so we haven't done the second part, right? Okay, so that's just the positive ones. Okay, the ones that are from above the x-axis, or the y-axis, right? To the left of the, or the right of the y-axis, the positive ones. Okay, now to see how many negative zeros there could be, the only difference is now what you have to do is you plug a negative x value in, okay, and then simplify it, and then see how many variations there are. Okay, so for this one, if I plug in a negative x into all of the x's, I have negative x to the 4th plus 6 times negative x to the 3rd plus 3 times negative x squared minus 2 times negative x plus 12. Okay, so if I simplify that, what would happen on the first term if I have a negative x to the 4th power? It's a positive, right? So this is a positive 12x to the 4th. What happens on the second term if I have a negative cubed? It's going to turn into a minus, right? So this one will be minus 6x cubed. What happens on my third term if I have a negative squared? Stays positive, so plus 3x squared. Okay. Oops, I missed my negative in there. If I have a negative, so I have minus a negative for that term. Positive. And then my 12 stays the same. Okay, so looking from the first to the second, is that a sign variation? Yes, it goes from a positive to a negative. Check, there's 1. What about from the second to the third? Is that a sign variation? Yes, 2. Count them 2. Third to the 4th? No. 4th to the 5th? No. Okay, so again, how many sign variations are there? So 2 sign variations. So again, that implies that how many negative zeros are there? Possibly. So there's either 2 or 0.
So they used to go through this whole process.
Yeah, I think that they used all these different tricks to eventually eliminate and conclude. I think, I mean, it probably depended on the function and how lucky they were at guessing initially, you know, but a lot of times zeros aren't nice whole numbers like 5. And in fact, very rarely are they. All the examples that I've given to you have been nice whole numbers. Okay, but not very often are they. A lot of times they turn into fractions. Okay, here's the very last piece of this, and this one's not too bad. We're almost done. You guys are doing a good job hanging in there. Okay, so this last example is something that you guys saw on the review and maybe you noticed on the quiz, the ones that I told you not to do because we hadn't covered that yet. So if you're given zeros, let's say you're given zeros. Okay, so your zeros are, let's say, -2. I'm going to keep it quite simple here, and the square root of 3. There we go. Okay, so if you're given zeros and asked to come up with a polynomial that creates those, first you're going to come up with the quantities that give you those zeros, and then potentially if they say specifically to write in standard form, you have to FOIL it all out. Okay, so what is the quantity that would give me a 0 of -2? X plus 2. Oops, I just wrote 3. 2. Good lord. Okay. What is the quantity that would give me a square root of 3? Oh, you guys are fast. Okay, everybody said x squared minus 3. So what does that imply? If you say x squared minus 3, what is the other 0 that's not written? There's a plus or minus 3. Okay, so absolutely you guys can go straight to the fact that this is x squared minus 3, and in fact, if you can do that, awesome. Okay, if you were saying it should have been just x minus the square root of 3, and using the linear quantity, then you would have to say, well, if there's a square root of 3, then there has to be a negative square root of 3 also. Those two things come in pairs. And it goes for square roots and for i's. Okay. So if we
Wait, so
foiled
which one is
this,
right?
well, they're the same. If I FOIL this piece right here, x times x is x squared. X times the square root of 3 is x square root of 3. Negative square root of 3 times x is minus x square root of 3. And a negative square root of 3 times positive square root of 3 is negative 3. Boom, boom, x squared minus 3. They're exactly the same. One's just already quickly done. Okay. Do I need to go over finishing this off and putting that into standard form? Is everybody good with that? Keep going?
Wait,
Okay.
what's standard?
So standard form means you can't have quantities. It has to be biggest exponent all the way down to the constant. So you'd have to FOIL. Yep, so you'd have x times x squared, so x cubed. X times negative 3 is negative 3x. 2 times x squared is 2x squared. 2 times negative 3 is negative 6. And then correctly putting those in the right order. Okay, you need to have biggest to smallest, x cubed plus 2x squared minus 3x minus 6. So that would be my polynomial with those particular zeros. That gives you the function with the zeros that are given to you. So if you type that into the calculator, that blue equation, it would cross at negative 2 and a square root of 3, and also a negative square root of 3. All right, so this is what I'm going to give to you guys. You're going to be on page 127. I'm going to cut the assignment in half. So I'm going to have you go 4 through 48 by 4s. Do not do problem number 40.